orthogonal theorem method. I start really abroad in my report, and I go narrower as I progress in my report. So first of all, I want to define what's orthogonal theorem. Orthogonal theorem basically is factors that have unit factor of length of 1, and they are linearly independent. And what I mean by linearly independent is it's when you have two matrices, you can represent one matrix in terms of the other by using the first matrix. For example, I want to go through each term so you guys can understand what these mean. So linearly independent, for example, if I have the matrix 2 and 3, and then the other matrix is 4 and 6. So I can represent this matrix in terms of that matrix, using that matrix without changing the magnitude for this matrix. And how is that? I can do 2 and 3, and then I can multiply by constant c. And in this case, the constant c is 2, so you will get the matrix again 4 and 6. So that's what's linearly independent. You can represent one matrix in terms of the other. And then have unit factor of 1, and again, what that means, if we have the triangle 3 and 4, and we try to find the magnitude for A, we will square both of these, so then we will have 3 squared plus 4 squared, and if we take the square root of that, that will give me 5. So these are not unit factor quantity. How I can make that unit factor? I can do some tricks. I can take the 3 divided by 5 plus 4 divided by 5, and if you guys square these two and take square root of that, you will get 25 divided by 25, and square root of that is 1. So these are unit factors now. Okay? Just wanted to write each there. So that's what that says. And if we're dealing with the angle, sines and cosine, it's sine and cosine is still unit factor. So if you take the square root of sine square and cosine square, you will get value of 1. So it's unit factor. Example. So they could ask us find the orthogonal basis for the set of vectors. So these two matrices are not orthogonal factor. And how I can know that? If you guys do dot product between them, you will not get value of 1. So these are not unit factor. But I can do some tricks to make them perpendicular to each other, and then find the orthogonal basis. So how we can do that? There is many methods online. You guys can look at them, and you can see the different process and how to use this method. But I'm really interested, I felt like Gram-Smith method is the easiest one to do to find the orthogonal basis, or make the matrix perpendicular to each other. So first, we will define phi1 as x1. So you will take the matrix x1 and set it equal to v1. And then you will solve for v2. And what v2 is x2 minus the projection of v2 and v1. What's like v? Okay, I don't need to open the light. If I have v1 and then I have like another factor v2 and it's not perpendicular to v1, I can project v2 and v1 and find the vector. Okay, so 90 degrees between the vector. Or we can do it by transpose method. We can do x2 minus x2 transpose multiplied by v1 divided by v1 transpose plus v2 multiplied by v1. And we study transpose, what's mean in structural analysis too. And if you guys forgot what's transpose, you take the row of the first matrix and convert it to the column. And that's the way you find the transpose. So that's the continual example. And now we found the v2, which is the vector perpendicular to V1. And they could ask us to find the arbitrary orthogonal basis, and that's the span for the two bases. And then the orthogonal basis is the arbitrary basis divided by the magnitude, and the magnitude is square of the square. All of us know how to do the magnitude. I mean, that's easy. And then orthogonal transformation. What's orthogonal transformation? What we're doing is either rotation or reflection. So if I have that line, Lx, which is passing through the origin and making alpha angle with the x-axis, if I have the factor x, I can reflect it across the line and find the other matrix. So I can find, like, Tx is the reflection for x across the line Lx. And then I can write the new matrix in terms of U and V set factor. So I didn't put the U, but the U will be parallel to the line Lx. So U, it will be this line. And then if you reflect U across Lx, nothing will happen because it's parallel to that line. And then the V is perpendicular to Lx, so if you reflect it, V will coming this way, so it will be minus V. And then we write U equal cosine and sine theta, and then V the minus because it will be in the negative y-axis. So orthogonal transformation. Okay, so the first one we wrote the matrix with respect to U and V unit factor. And now we want to write it in terms of the standard unit factor. So if we are given the M value, which is U and V value, and then and write them in terms of cosine and sine, we want to find these matrices with respect to standard unit factors. So the identity ID. So we will go cross ID dot M dot ID, and we find M the new unit factor M dash. So I and ID will be equal to each other, but they are transpose for each other. So this will be same with changing sign, and that will be same with changing the sign. Not transpose, inverse for each other. So then I go like I took that right out from our structure analysis one, and I thought we dealing with orthogonal theorem a lot in our major, but we weren't attention. So if we trying to find the force transformation matrix, so if we have the force Q and X, or let's say Q in general, and Q is parallel to the local axis X dash, we can break it into components to be easy to find the equations. So perpendicular, like component perpendicular to that local axis. We basically transfer from local to global in here. And then same thing if we have the Q parallel to the Y local axis, we can break it in component Y and X and write these in terms of sine and cosine angles. And this angle will be, theta X will be same as this angle, and that angle will be same as this angle. And we write the equations. And notice that X and Z and Q and Z are equal to each other. And why is that? Because the direction of Z into the page, so they are collinear to each other. And then we write that in terms of matrix, and that's what we were doing in our homework in structure analysis. So we writing matrix and solve for the equation. It's easy to deal with number instead of variables. And same thing if we're doing displacement. So if we have the displacement parallel to the local x-axis, we can break it into components and find the equation first for equation for the first picture, and then the second-order equation for the second dictionary. And then write it in terms of transpose. And what's lambda? Lambda, I defined it as cosine theta x and cosine lambda y cosine theta y. So I just summary what we're doing in structure analysis. So structure analysis, we basically deal with a lot of boundary condition, a lot of superposition and stuff. We're dealing with structure and shear strain relationship and deflection, moment, and all of that. We basically dealing with linear vectors and orthogonal. So I thought it's a really cool idea to go and ask one of my professors. He's my dynamics professor and he's aerospace engineer. So I asked him how the orthogonal factor and linear factor help them in their measure and stuff. So I would like you guys to hear to what he's saying and his opinion. And it's only 2-minute video. So, and then I will go over the question if you guys have questions. Oh no. That's the one.
Can you turn the volume up?
Hit escape and run it out of the PowerPoint mode.
I think it's working.
There it goes.
How do you turn volume?
Turn it way up.
Oh.
So as you're aware, you can extract the... I work in structural dynamics and acoustics, and orthogonal solutions and methods based on that are very useful to solve several problems. One of the things that we use quite often is what is called the method of normal modes. So as you're aware, you can extract the natural frequency and higher frequencies of the eigenvalue analysis. These result in certain vector solutions. Now, you can characterize motion, complicated motion of structures, and these would be very complicated structures, by superposition of these different normal modes. What we're saying is each of these responses are orthogonal vectors, and then by combinations of these modes, you can characterize the overall response of the structure to some random excitation or some non-standard excitation and so on, right? So this is a powerful method because you only need to be able to discern what the participation factors are of each of these modes in order to be able to predict the overall response of the structure. For example, if you have in a very simple case, some kind of a plate-like structure, or in our case we use membranes, trying to see how we can improve the acoustic transmissibility of lightweight structures. Now, one of the problems that we have is we can't add mass to structures like aircraft structures because that defeats the purpose. So we have to choose something like a lightweight structure and tune those resonances of these lightweight structures like membranes in order to cancel out certain spectrums of sound. So then you can look at each of the modes or the modal responses of these membrane-type structures as orthogonal vectors, and then the overall response can be compiled as a combination of these normal vectors. So that solution technique is used very often not only for these kinds of lightweight structures, but also in several analysis of nonlinear structures, which is also a new direction that we are trying to employ. For example, in many structural applications, you sort of do not consider nonlinearity. In fact, you try to avoid nonlinearity. But what we're trying to see is if we can take advantage of nonlinear response in enhancing the performance of structures. Even there, we have the application of the orthogonality theorem, method of normal modes, applied perturbation analysis, which is sort of multiple scales. So those are some of the things that I'm working on now that I think may be sort of slightly linked with what you're doing.